Hello and welcome, everybody. My name is Adam Richardson. I'm going to be your professor for Calculus 2 this term. I'm really excited to get started with all of this stuff. Calculus 2 is one of my favorite courses now. I should say that I didn't really like it when I took it as an undergrad, but hopefully I can make your experience a little bit better. In retrospect, or just later on, I grew to love Calculus 2, and it's my favorite of the calculus sequence. Although I guess it's kind of a toss-up between this and Calc 3. I hope many of you are going to take Calc 3 next semester because it's just even more amazing. Calc 3 is like taking everything that you learn in Calc 1 and Calc 2 and elevating it to higher dimensions. It's just so cool and so fruitful. Um, this lecture here, this lesson is basically a kind of a review of some important pre-calculus concepts and some Calc 1 concepts. One thing I have to admit is this lecture is particularly long. The lectures are not normally as long as this one is going to be, but it's really hard to encapsulate everything that you would want to review from pre-calculus and Calc 1 in just like a short video. It is broken up into three parts, though. So there's a pre-calculus part, a differential calculus part, and an integral calculus part. So you can take breaks in between. This also doesn't cover everything that you need to know, but there are some particular concepts that I wanted to at least emphasize before we get started with Calc 2. Another thing I will say is I'm going to move quickly through a lot of these slides, so don't feel don't feel overwhelmed or feel rushed. Um, you can always review the slides again in the future. Some of these things I know you have seen already in the past and you probably know very well. But I just wanted to have kind of a quick, or maybe just not a quick, but like an overview of things that you kind of want to know about to do well in Calculus 2 and to make deep intuitive sense of the things that we're going to learn in Calculus 2. So I'll stop rambling and I'll throw up these slides. Here we go. So it's a lot of slides, I know, and I know for those of you that have taken me before, you're like, "Oh, MG, it's 99 slides. That's impossible." Again, it's a lot of stuff, but remember, you can take breaks, you can pause, you can watch the video at double speed or whatever you want, and then I'll sound really like a chipmunk. But it's just kind of a repository of a bunch of information, all right? Some I'm going to dwell on, some I'm not. So here's the overview of the entire lesson. Part 1 is pre-calculus review. Part 2 is differential calculus review, and part 3 is integral calculus review. Shouldn't even, well, actually, no, it is kind of an intro. I just called it integral calculus, though. All right, so let's go to part 1, pre-calculus. Let's go back to pre-calculus for a bit and talk about some things. Actually, well, I'll say this. Here's the overview of this part of the lesson. We're going to look at some fundamental ideas about the basic operations. Um, I actually go over these ideas in all of my math courses, even though they are essentially elementary school level ideas. But what I found in my own research is that having a deep understanding and intuition of these basic ideas can really help you make sense of the more advanced, complex mathematical ideas that we'll see in this course and beyond. So I want to talk about a fundamental intuition of those operations. We're going to briefly review the properties of exponents, talk about functions and what functions are. We're going to review absolute value, talk about polynomials. We're also going to talk about the Weierstrass approximation theorem. This is a really important theorem about polynomials that I think should be discussed in every pre-calculus class. I also discuss it in my Calc 1 class as well, and we will discuss it in this class. It's just a really important theorem. We're also going to briefly talk about the fundamental theorem of algebra and an important corollary of that theorem. Generally speaking, any theorem in mathematics that is called fundamental blank, you should know what it is and understand what it's really saying. We'll briefly review the polynomial division algorithm because we are going to need that in this course. I'll talk about some basic graphs that you should have memorized, graphs of sinusoidal functions. This one I'm going to do a specific example for because we are going to be graphing sine and cosine functions and their transformations in this class. So I wanted to review it at least a little bit. I will also briefly talk about inverse trig functions, although I go into more detail in the section on inverse trig functions in this class, so I won't dwell on them for too long. And then we'll finish up with, we'll finish up with sequences and series, where I'll just kind of review those things. So that's pre-calculus. Let's get started. Um, so let's just talk about the fundamental intuition of addition and subtraction. Again, I'm not trying to be patronizing here. I'm not trying to say you don't know what addition and subtraction is. I'm just saying that reviewing these very basic ideas can help you make sense of deeper mathematics. So when you get stuck looking at some crazy complicated formula, if it involves addition or subtraction, you can always go back to this intuition to help guide you through the mathematics. So what is addition? Addition quite literally means to bring together or combine objects. So when you think of addition and when you see the addition sign, you should think about bringing together two quantities. That's really what it is. What is subtraction? Subtraction is removing one quantity from another. So subtraction is like an excising, an excising process. It's like you're reaching in and taking something out. That's what subtraction means. Um, Multiplication. So multiplication is simply repeated addition. It's repeated addition. That's actually one of the reasons we use this symbol for it when you're first learning it as kids, right? Because it's basically a plus sign that's been rotated a little bit. So it's related to addition in the sense that multiplication is just repeated addition. So when you think of multiplication, you can think of it as adding something a certain number of times. And again, this intuition holds for any multiplication that you'll ever see or ever work with. That's what multiplication means. So 3 times 6 means adding 3 6 times. 14 times 5 means adding 14 5 times. 8x means adding x 8 times, for example. That's basically what multiplication is. Kind of on the inverse side of things, division is actually repeated subtraction. So that's really what division is doing. It's saying repeatedly remove something over and over and over again a certain number of times, right? So subtraction is the inverse of addition. Division is the inverse of multiplication. It's just you're doing that more than one time or any number of times. So that's what division really means. Um, Symbols for it, the division symbol or the fraction symbol, which we'll talk about in a minute. Another way you can interpret division is that this symbol a divided by b means to cut up a into b groups. And so a divided by b is how many things are in each group. That's another way of interpreting it. Um, I find this particular interpretation of division in this symbol to be extremely helpful. Extremely helpful. So I hope it helps you. Whenever you see a fraction like a over b or anything over anything, you can think of it as the answer to this question. So this symbol is the answer to this question. How many times does the denominator fit inside the numerator? How many times does b fit inside a? That's what this symbol means. For a really, really nice example, let's look at this. 3 over 2. What does 3 over 2 really mean? It means how many times does 2 fit inside of 3? Well, let's count. 2 fits inside of 3 once, and then it fits inside of 3 another half of a time, right? Not a full time, but like a half of a time. Well, that's why 3 over 2 is equal to 1.5. It's 1.5 because 2 fits inside 3 one whole time, and then also another half of a time. That's the idea. And again, this holds for any fraction that you've ever seen in your life. So anytime you see a fraction, say this phrase out loud to yourself, and it'll completely change the way that you interpret that fraction. How many times does the bottom fit inside the top? And that's what that symbol means. Ponder it for a bit. Okay. Another important interpretation is this. So when you see a over b, it is equivalent to saying 1 over b a times. So that's how it's related to multiplication. It's really just adding the number 1 over b a times. It makes more sense when a is an actual integer, right? So even though we're talking about multiplication as times, it can be extended to partial times, as we'll talk about in a bit. But for intuition, just think of it as 1 over b this many times, all right? Okay. Oh yeah, so what is 3/4? 3/4, for example, is quite literally 3/4. It's 3/4, 3 1/4. Okay. Um, Now an important one. So let's talk about Exponentiation. So exponentiation is repeated multiplication, and we use a little superscript to indicate that process. So whenever you see a superscript like that, what we're talking about is doing this product, or I should say multiplying this number by itself n many times. So for example, 2 to the 6th is 2 times 2 times 2 times 2 times 2 times 2, 6 times. That's what that symbol means. Now, here's the big idea, and this is going to help you out a lot, so take this one to heart. Exponents count multiplication. They count factors. And the reason that it's good to think about it in those terms is because that fundamental intuition extends to non-integer exponents. So if you've got something like, you know, x to the 1/3 or x to the 5 seconds, like 5 halves, that exponent is still counting multiplication. It's just now it's counting parts of a product. So if I have like x to the 5 halves, well, that's x to the 2.5. That means there's 2 whole factors of x and then 1/2 of a factor of x. In other words, square root of x. Let me write that down real quick. So like x to the 5 halves, that's x to the 2.5, which is x squared times root x. Before I jump the gun too much, x to the 1/2, which is x squared root x. There you go. So how many x's do I have? I've got 2.5 of them. There's 2, there's the half. Except now we're speaking multiplicatively, right? When I say that, how many of do we have? I'm thinking multiplicatively. So carry that with you whenever you look at an exponent, and it will help out quite a bit. And on that note, here's a quick refresher of the properties of exponents. I'm not going to go into much detail about these. Hopefully you have a decent amount of experience with them now. You need to be really, really comfortable with these properties of exponents because we're going to use them all the time, especially when we get to sequences and series. A lot of what you do in sequences and series, at least algebraically speaking, is manipulating exponents and exponential factors and things that look like exponents. All right, so basic properties, go through, review all of these, make sure you're comfortable with all of these. We use these two a lot when we get to sequences and series. And this is literally how you convert from radicals to exponents. Hopefully you talked about that in Calc 1. Okay, here's a good example. Maybe you should try this one on your own. So what I like to do with my lectures is this. When I have an example that I want you to try at home, I will usually throw up a couple emoji for you to take note of, or to indicate that you should do this on your own. The first one is this one, which I call the thinker. And the thinker means I want you to think about what this question is asking you to do. And then after I throw up the thinker, I usually like to throw up the thinker and the speaker. And when I use these emoji, I want you, or in particular the speaker one, I want you to say something out loud. All right, say something out loud. And it just has to be out loud. It doesn't have, nobody has to be with you. You could say it to yourself, you could say it to your dog, or to your sisters, or your brothers, your family, to your shoes, to your hand. Just say something out loud to give your brain that feedback, to give your brain the feedback of what you're saying. And then I like to throw up the thinker and the writer. So this is when you should actually try to do the calculation, do the problem, and solve it, or just do whatever the problem is asking. And then I'll usually go back and we'll do the examples together. All right. So let's try it this time. Here's what I want you to do. I want you to try to factor this. So factor this expression. And first, I'm going to throw up the thinker. What would you do first? What do you think you could factor out? All right, now I want you to say something out loud to yourself. Just say out loud to yourself what you could factor out of both of these terms. All right, now try to work it out on your own. Factor it, and then we're going to do an example together right now. All right, here we go. So what is a common factor to both of these terms? Well, there's an x to the 1/3. So each one of the, well, actually, I should say this. There's two terms in this expression. There's this one and this one. And both of those terms have a common factor of x to the 1/3. Remember, exponents are just counting multiplications. So This is 1/3 of x, and this is 4/3 x's. Well, if I've got 4/3 x's, I've definitely got 1/3 x's, so I can factor those out. And here's how it goes. And again, use that intuition, use that fundamental intuition for exponentiation. When I factor out x to the 1/3, what's left is, well, it's completely gone from this term, but over here, I had 4/3 and I took away 1/3. So that means I have 3/3 left. And what's 3/3? It's 1. So you get x to the 1. So this expression factors into this, which you can then simplify to this. And then if you would like, you could rewrite it in terms of radical notation right here, like so. All right. Okay. Oh yeah, now let's talk a little bit about functions. So when I talk about functions in pre-calc and calc 1, I like to do it in a very, very general way because the concept of a function is like the most important concept that you want to feel comfortable with in order to do advanced, sorry, typo there, advanced mathematics. So briefly speaking, a function is just a rule that assigns to each element x in a set D exactly one element called f of x in a set R called the range. And one thing I want to point out here is notice that this definition says nothing about numbers. It says nothing about numbers whatsoever. But numbers are easy to play with. And so oftentimes when we talk about functions, we use numbers because things are very clean when you use numbers. They're easy to follow. They're easy to make sense of. But functions don't have to be numbers. I'm sorry, they don't have to handle just numbers. And in fact, you have seen, and we will see, other functions that don't handle numbers. They handle other things like other functions or sets or something like that. All right. Generally speaking, a function is just like a box, literally a box that transforms objects into new objects based on some rule that we call f. Okay, so here's the picture of it, just like so. So what happens here is you take x, you drop x into the box, it gets f'd up, and what comes out is an f'd up x. F of x is what we call it. Now, here's the one requirement. The one requirement of a function is that only one object can come out of the box at a time. That's the object that we call f of x. So if you put an object into the box and it spits out like, 2 or 3 or any number more than one object, then you don't have a function at that point. Oh, hold on. My daughter's sneaking in on me. What is it, sweetheart?
Daddy,
What?
I'm watching the show.
Oh, what show are you watching?
Hammer Barn.
Oh, Hammer Barn. She's really into Bluey right now, and we have like a book where we read stories from the show, so it's pretty cool. Bye, sweetheart. Anyway, what was I saying? Oh yeah, functions. Oh yeah. So you can't have more than one object come out of the box at any time, and if you do, you don't have a function. The box is not a function. Now, I do want to dwell a little bit on the notation of a function. Again, I'm not trying to be patronizing. I know many of you are probably experts at this notation, but it behooves us to talk about this notation a bit more because in my experience, when students are struggling with functions, it's because they're not really grasping what the notation represents well enough. So here's the idea. The symbol here is representing the input. The symbol doesn't have to be an X, it doesn't have to be a Y, it doesn't have to be a letter, it doesn't have to be a number, it can be anything. It can be any symbol you want to use to represent the object that you're going to put into the box. All right? Now, this part of the notation is the label for the name, or I'm sorry, the label for the rule of the function. So this letter quite literally is representing what the box does, right? It's representing the process, the process. So the function itself is that process, and the function is indicated with this letter F right here. All right. And now here's the big takeaway. Here's the important part that you really, really want to make sense of. The entire symbol is representing the output of the function. So f of x is not the function, it's the output of the function. Okay, f of x is what comes out of the box. It's not the box itself. There's a distinction there. It's a very, very important distinction. F is the label on the box. F of x is what's coming out of the box. Okay, that's the idea. So for example, take the function f of x equals 3x plus 1. Well, x is the input. There it is. And f is the rule given by this sentence right here. The letter f here is representing the sentence multiply by 3 and then add 1. Okay, so this letter F is telling you what the box is going to do. And what is the box going to do? It's going to multiply the input by 3, and then it's going to add 1 to that result. Then 3x plus 1, that's the output. That's the thing that comes out of the box after you've multiplied the input by 3 and then added 1. So what falls out of the box is f of x, okay? That's the idea. F of x is the output of the function, not the function itself. Okay, keep that in mind. All right. Some other little details. The domain of a function is the set of all the input elements that work. So in other words, the domain is it's the set of things that the function can actually process, right? You don't want to put things into the box that are going to break the box. So if something is going to break the box, it's not in the domain of the box, not in the domain of the function. Cut that thing out, okay? The range is the set of all possible outputs. So the range is literally the collection of anything that could possibly come out of the box given an input. That's what the range is. And then there's another set. I'm not sure if your pre-calculus teachers talk to you about this, but there's another set called the codomain of the function. And the codomain is the set or the space that contains the range. So the codomain is basically sometimes a bigger set than the range because even though your function might map real numbers to real numbers, it may not map to all of the real numbers. Let me give you an example. Easy example is f of x equals x squared, right? So x squared takes any real number and it maps it to the interval 0 to infinity. Okay, so this is the range. This is the domain, but the range lives in the real numbers. So here's a picture of it, right? Everyone knows what x squared looks like, right? Okay, so what's happening is we're taking real numbers and mapping them to the set of positive numbers or non-negative numbers. But we're missing all of the negative numbers, right? So what is the codomain? The codomain is the whole real line. So the codomain is R, and that's where your range lives, even though the range is not equal to R. It's just where it lives. All right. Another important concept, even and odd functions. So some functions are even, some functions are odd, and you want to know about these definitions. A function is even if when you change the sign of the input, it doesn't change the sign of the output. That's an even function, okay? Classic examples are cosine. Cosine is an even function. Uh, X squared is an even function. And what's nice about even functions is they're symmetric about the y-axis. That's the symmetry involved with even functions. Odd functions. So odd functions are different. Odd functions are functions where if you change the sign of the input, it changes the sign of the output. So here's classic examples. The sine function is odd. Here's the function x cubed minus 2x. That one's also odd. Okay. What's nice about odd functions is they are symmetric about the origin. Symmetric about the origin. That's what's going on. So there's the symmetry there. It's not through a line, it's through a point. It's like everything is getting mirrored through the origin, like so. That's an odd function. Okay, the next thing I want to go over is, come on, there we go, is absolute value. So it is important to really, really have a good understanding of what absolute value is. Strictly or simply speaking, absolute value is just the distance away from 0 for some real number. All right, so you can think about it as the size of a number. That's really what absolute value is telling you. It's telling you the size of a number. Now, what's important about absolute value, at least as a function, is how it works. How it works. And I'm really hoping that your pre-calculus teachers talk to you about it because I know mine didn't really, and my high school teachers didn't really. They just said absolute value makes everything positive, which is true, which is true. Absolute value makes everything positive. But how does it do that? How does that function? How does that rule? How does that process actually make things positive? This is how, okay? And the idea here is if the number that you put into that function is already positive or non-negative, then the function will just spit out the number again. So if you put in 8, it's going to spit out 8 because it's already a positive number or non-negative number. But if the thing that you put into the box is a negative number, then what this rule will do is take the opposite of that negative number, which will make the result positive. So if I put in -2 to the absolute value function, what the absolute value function is gonna do is take the opposite of -2, which will give me +2. That's how absolute value works. Okay. Now, here's a really important concept, and you use this a lot in Calc 1, you use it a lot in Calc 2 as well, and you'll use it a lot just in general, but the distance between two numbers is given by this expression. So the absolute value of a difference literally is the distance between two numbers. So when you see something like 9 minus 3 in absolute value, that is the distance between 9 and 3, which is 6. What is absolute value of 7 plus 10? Well, that's the distance between 7 and -10, which is 17. So it's the distance between 7 and -10. That's 17. Now, here's what's also cute, right? So if you look at just absolute value of x, you can rewrite it equivalently as absolute value of x minus 0, and that's the distance between x and 0, which is the definition of absolute value, the distance from the origin. So in some senses, this is like a special case of this function right here. That's kind of how it goes. Okay, so that's absolute value. Now let's talk about polynomials. So you spend a decent amount of time in pre-calc and before talking about polynomials. There's good reason for it, and we're going to see it in great detail in this class, but hopefully you also saw it in pre-calc and calc 1. Just a refresher, polynomials are functions that have this structure. They are linear combinations of power functions, meaning you're going to add up a bunch of power functions, but you're also allowed to multiply those power functions by coefficients, constant coefficients. The coefficients are real numbers, or they could be complex numbers if you're working in the complex numbers, and you're just adding all those terms up. That's what a polynomial is. The degree of a polynomial is the highest power. So in this case, the degree would be n, the exponent of the leading term. And another nice thing about polynomials that we love, love, love is their domain is all real numbers. So they're defined on all real numbers. Okay, so why do we care about polynomials so much? We care about them because of this theorem. So this is a really important theorem, the Weierstrass approximation theorem. And it basically says this. I'll read it out loud and then I'll give you some intuition for it. Suppose you have a continuous real-valued function defined on a closed interval a to b. Then for every epsilon greater than 0, there exists a polynomial function p such that for all x in that interval, the distance between f of x and p of x is less than epsilon. Okay, so this is one of those times where I'm actually going to throw up the thinker, and I want you to think about what I said for just a moment. Okay, now I'm going to put up the speaker, and I want you to read this out loud to yourself. Read this out loud, and then read this second bullet point out loud to yourself. Okay, read it out loud, give yourself that feedback. Okay. Now let's talk about it some more. Let's take apart what this theorem is really saying. Epsilon is often what we call a tolerance or an error. You can think of it as how far off you're allowed to be. In particular, how far off the difference between the outputs of F and the outputs of P are allowed to be, the distance between those outputs. That's what this symbol is representing, the distance between the outputs of those two functions. And the reason this is such a powerful theorem is because this says that if you've got any continuous function on a closed interval, then there exists a polynomial function that approximates that function f as close as you want, as close as you want. That's really what it's saying. So why is this so helpful? Well, let's say you've got a really nasty but still continuous function. and you have to do some kind of analysis on it or do some kind of work with it. Well, you don't really want to have to work with such a pathological function, such a sick function. So if you're okay with introducing a tiny bit of error, a tiny bit of error, epsilon. Epsilon is a very, very tiny number. Think like 1 over 1 trillion billion quadrillion, like tiny, tiny, tiny number. If you're allowed a tiny bit of error, then we can find you a polynomial that'll be so close to your function that it'll only differ from your function by that tiny, tiny, tiny little bit amount. That's what this is saying. Really, really powerful result. All you need is continuity. All you need is continuity on a closed interval, and there's an approximating polynomial. That's what it means. Why is this so helpful? Computers are excellent at producing, factoring, and generally working with polynomials. So if you can convert your work into polynomial land, you just saved yourself a lot of problems. You just saved yourself a lot of headaches. Okay. Another reason we love polynomials is because of the fundamental theorem of algebra and an important corollary. So here's the fundamental theorem of algebra. It says that every non-constant single variable polynomial with complex coefficients has at least one complex root. Okay, now this is one thing I have to admit is that this particular theorem is very terse and very concise. That's one of the reasons it's such a powerful theorem, because you don't really have to say much to get a very large result. This is just saying that you're always going to have a complex root. Every polynomial has at least one root. That's what it's saying, as long as you allow complex numbers. Okay. Now, why is this why is this so important for us? Well, you get this really, really powerful corollary here. A corollary is like it's like a small, or it's a related result that follows from a big theorem. So the fundamental theorem of algebra is a big theorem with wide-ranging consequences. Here's one of the consequences, and this might kind of like make you crook your head a little bit when you hear it at first, but it says this: every polynomial function with real coefficients can be uniquely factored into products of powers of linear factors or irreducible quadratic factors. Okay? So what this is saying is, hey, do you have a polynomial? Guess what? If it's, do you have a polynomial? It can be factored. Yes, it can be factored. So if you think back to those times when you had some polynomial that was like x to the fifth, blah, 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 and you were like, oh man, does that factor? The answer is yes. Yes, by the fundamental theorem of algebra. And if you're forced to stick with only real coefficients, like if you're stuck with real numbers, then you can always factor until you get down to factors that are linear or quadratic. So look like mx plus b, or look like ax squared plus bx plus c. That's a result of the fundamental theorem of algebra. And what's even better is if you allow yourself to work over the complex numbers, then you can keep factoring until all you're left with is a bunch of linear factors, meaning like mx plus b, mx plus b, mx plus b, mx plus b, literally. So it's a really, really powerful result. So yeah, if your polynomial is degree 3 or more, it can be factored over the real numbers. So if you got x to the fourth, blah, 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 yeah, it factors. It can be factored by the fundamental theorem of algebra. All right. One of the ways that you explore how to factor things is through division, because division is essentially factoring, except division is a more general form of factoring because not every number is a factor of another number, right? And you explore this in detail when you learn the polynomial division algorithm. So this is what some students like to call, or just people like to call, long division. Because there is like a short division, but I like to call it the polynomial division algorithm because this is really what it's saying. So the polynomial division algorithm is an algorithm that lets you calculate remainders when you try to divide by certain factors. So let's say you've got p of x and q of x, they're polynomial functions, and we know that the degree of q is positive or non-negative at least. Then the polynomial division algorithm says this division will yield a function f, and actually, I'm sorry, a polynomial f and a polynomial r, such that your rational function is equal to this polynomial plus this difference function here, is what I'll say. Um, Do I say it here? I don't say it here, but this is something that I go into great detail about in my pre-calculus class. When you do the division algorithm, or like if you've got a rational function, here's the amazing part. This polynomial that you get as a result is the asymptote of your function. It's the non-vertical asymptote. And this piece right here is a difference function, which means this piece tells you how far away you're going to move from this asymptote. So if you remember back from the sections that every student hates where you have to graph rational functions and you had to do all these manipulations, well, it's much easier if you simply just do the division algorithm, because the division algorithm reveals all of the structure of your function. It reveals the asymptote and how far away you're going to move from that asymptote, right? What I'm going to do is do one example here. So I'm just going to show you how the division algorithm works. We'll have to use it at some point in this class when we get to partial fraction decomposition, but here's how it goes. Yeah, here's the calculation. The degree of the numerator is greater than or equal to the denominator, so we can actually use the division algorithm. And this is about what it looks like here. If you remember, you basically ask yourself, what do you need to multiply this by to get this? And in this case, it's x. So x times x squared equals x cubed. X times negative 9x is negative 9x squared. X times 7 is 7x. And then you go through and you change all the signs to get this, right? Then you subtract and you're left with this. And then you repeat the process. You keep repeating the process until the degree of this result is less than the degree of this result. So that's the division right there. But lo and behold, what this really says, what the polynomial division algorithm is saying is that, hey, this function is equal to an asymptote plus a difference function. So if you want to graph this function, you can graph it by first graphing its asymptote, x plus 5, which looks like this, right? And then from that, you can basically see how it relates to that slanted line. There might be some, there might be some vertical asymptotes. There might be some holes. There's all sorts of things that could happen. But this line here, x plus 5, that's the non-vertical asymptote. And this function here, the remainder piece, it's not really the remainder, it's like a difference function. This tells you how far up or down you're going to move from this asymptote. Cool stuff. Cool stuff. Okay, speaking of graphs, this is a list of basic graphs that you should have memorized. I didn't include them on the slides because they're frankly just like standard graphs. I'm sure you know most of them. If not, you do want to get comfortable with them because they'll just pop out of nowhere, and you have to be able to recognize what they are, what they look like, including their transformations. So I'll just read the list. You can go graph them on Desmos on your own if you would like, but here's the list. Constant functions. So the function y equals b for any real number b, horizontal lines, constant functions. F of x equals x. That's what we call the identity function. This is the function where whatever input you put in, it just spits it back out again. No change. No change whatsoever. It's just input is the output. Power functions. So x to the a for any a greater than or equal to 0. This means x squared, x cubed, x to the 4th, x to the 5th, x to the 7th. You should be comfortable with those graphs, able to draw a quick sketch of those graphs at a moment's notice. Even things like, well, yeah. I'll say even things like fractionals as well. So like x to the 1.3, you should be able to graph that. It's going to be like in between x squared. I'm sorry, x and x squared, or any of those. So you should be comfortable with those types of functions. Same for the reciprocals of the power functions, right? These ones have an asymptote at 0, a vertical asymptote at 0, but they all basically resemble 1 over x or 1 over x squared. You also want to be comfortable with the the root functions. So this is when you have things like square root of x, cube root of x, fourth root of x, fifth root of x, and so on. You should know roughly what those graphs look like. You should definitely know the absolute value graph. That's the v, right? That's the big V. This one is the formula for a circle centered at the point h comma k, with radius r, you definitely want to know that formula because we will see that everywhere, everywhere. And then not only do you want to know the equation for the um, equation for the circle, you also want to know the functions for the top and the bottom and the left and the right. That's what those are right there. So again, I'm not going to dwell on those. I'm hoping that you're comfortable with those. If not, you definitely want to review those because they will pop up everywhere all the time. Okay. Oh yeah, so now this is an example that I do want to do. So graphs of sinusoidal functions, we are going to need to graph functions like sine and cosine and their transformations when we get to the section on polar coordinates. I already have 2 lectures recorded for my trigonometry course that go into all the details of how to graph these types of functions and their transformations. So if you would like, you can review them here. Just click on the links and it will take you to those videos on my YouTube channel. There's one proposition that identifies all the data that you need to do these graphs, and it's right here. So if you've got a sinusoidal function like so or like so, then the amplitude is this, the period is 2 pi over omega, the phase shift is phi over omega, and when you're graphing, your key points are going to lie at these points right here. So this is basically just how to graph these functions, and you go through this all when you take a trigonometry course or a precalculus course. I'm going to do one example just to show you all here so you don't have to go watch those other videos, but if you do want more examples, you can watch those other videos. So here we go. Let's find the amplitude, the period, the phase shift, and the midline of this function, and we're going to graph it, okay? So here's the function. It's a sinusoidal curve. Just by looking at the structure of the function, we can immediately see that the amplitude is 3. The period is going to be pi because in this case, omega is 2. The period of sine is 2 pi, so the period of this transformation is 2 pi divided by 2, which is pi. There's a phase shift. The phase shift is going to be phi over omega, so this number divided by this number, pi over 2. So basically the whole graph is shifted by pi over 2 units to the right. And then we have the midline. The midline is basically where the graph is kind of centered, right? And that's given by this vertical shift component right there. Okay, so with all this information, we can also find the key points. How do you find the key points? You take your period and you divide it by 4. So our period is pi, and when you divide pi by 4, you get pi over 4. So all of our key points are going to be at the phase shift plus multiple integer multiples of the period divided by 4. So phase shift plus pi over 4, I should say this, phase shift plus 0 pi over 4, phase shift plus 1 pi over 4, phase shift plus 2 pi over 4, and so on and so on. That's how you get the key points. Now you can graph, and there it is. So the midline is 1. The amplitude was 3, so we go up 3 and down 3. Here's the phase shift. We moved the whole graph to the right by pi over 2. And then those key points are these ones right here. This is why you do the period divided by 4, because it'll tell you where this, and this go. And then you have the initial point at the phase shift. Okay, that's the idea. Okay, now a brief mention of inverse trig functions. We're going to review these a lot more in section 6.6, so I'm not going to dwell on them here. We'll get to that lecture in like a few sections. But I also have a complete lecture, or 2 complete lectures, on inverse trig functions from my trigonometry course here and here. So you're also welcome to watch those if you need a refresher. I didn't include it here, but I have another lecture on just inverse functions in general on my, for my Math 3 course, and I believe it's section 4.1. So you can watch that there as well, if you need just a general review of inverse functions. Okay. All right, now let's talk a little bit about sequences. This is another one that I'm not going to dwell on for very long because we will review it at length when we get to chapter 11. But a sequence is just a function, except it's a function whose domain is the positive integers. That's it. That's really it. That's what a sequence is. It's a sequence it's a function that's domain is the positive integers. So technically these are all the outputs of a sequence, but instead of writing it like that, we often adopt the convention of writing it like this. So these are the outputs of that function. And in other words, it's just a list of numbers. So a sequence is just a list of numbers. There's a first, a second, a third, a fourth, a fifth. It's just a list of numbers. That's all it is. But what you're doing is you're saying, hey, take the number 1 and map it to this output, and take the number 2 and map it to this output, and take the number 3 and map it to this output. It's a function. Okay. Some notation. Oh, sequences can have finitely many terms or infinitely many terms. Here's the notation for sequences. This is like an infinite sequence. Dot, dot, dot means it keeps going. This is the index. N is called the index here. It's just telling you how you're going to count. And then the upper bound there is how far it goes. So with finite sequences, the sequence terminates at some point. For infinite sequences, it doesn't. It keeps going on forever, quote unquote. A sub n is called the nth term of the sequence, and a sub 1 is called the initial term, like the first term. All right, now let's talk about series and sigma notation. Again, I know that this is maybe overwhelming. Don't feel like you need to just suddenly digest all of this instantly. It's just kind of a review. We will talk more about these as the course goes on, but these are concepts that you hopefully have explored a little bit in the past, right? The past. So that's why I'm going through them now. A lot of times we want to add up the terms of a sequence and see what the result is. This is what's called a partial sum. And in order to simplify our lives, we have a notation for adding things up called sigma notation, and it's this right here. That this letter right here is the Greek letter sigma, which or Greek letter S, capital S. And the reason that we chose it is because it suggests a summation. It suggests adding a bunch of stuff, all right? The integer, oops, sorry, this should say K. The integer K is called the index. You can use whatever letter you want for the index. I used K right here. Okay. So what is a series? So a series or an infinite series is just an infinite summation. So basically, a lot of times, especially in this class, we are going to be very interested in what happens when you add up infinitely many terms of a certain type. And this sequence can follow all sorts of patterns or no pattern. We want to know, hey, if you add all these things up, do you get anything or do you just get infinity? It might surprise you to know that you don't always get infinity when you add up infinitely many things. Sometimes you get a finite number. Sometimes you don't get any number. Sometimes you get infinity. Sometimes you get negative infinity. There's lots of possibilities. Lots of possibilities. So if it turns out that this adds up to an actual number, we call that number the sum of the series. And the sum of the series is defined as the limit of the partial sums. So it's the limit as n goes to infinity of these truncated series, And you look at what that limit is, and if that limit exists as a finite number, then you say the series is equal to that number. All right? We'll go through that in more detail when we get to chapter 11. But on that note, it's time to take a break. So this is a good point to pause. We're going to get into differential calculus next, but let's just pause for a moment. I really need some like elevator music to play, like Okay, all right. So welcome back, everybody. I hope you took a little bit of a break. Now I'm going to go on to part 2. This is basically some stuff that you want to remember or recall from Calc 1. I split this into 2 parts, differential calculus and integral calculus, because they're different kinds of calculus, and it's good to distinguish between the two. So here's the overview for differential calculus. We're going to review the limit of a function at a number, the limit of a function at infinity, the general limit laws, the squeeze theorem, the derivative, the differential operator. I'm going to focus on that a little bit. The differentiation rules, everyone's favorites, linear approximations, because we're going to expound upon those in this class, and then the idea of transcendental numbers and transcendental functions. So that's what I'm going to talk about here with the differential calculus. Okay, So first, the limit of a function at a number. I'm not going to dwell too much on this because this is something that you spend a significant amount of time doing in Calc 1. But here's the definition of it. This is like the intuitive definition. What we say is that I should say this. We write this symbol if we can make the values, the outputs of f, arbitrarily close to this number by taking x to be sufficiently close to a. So basically, as x approaches some number a, what are the outputs that your function goes to as you approach? And if that limit exists, then there's a number that those outputs go to, and that's what the limit is. All right. But remember, the limit does not always exist. The limit doesn't always exist. This is critical, and you focus on this a lot in Calc 1. Sometimes, as x moves closer to a, f of x moves back and forth and won't converge to any point. And a classic example is this one, sine of 1 over x. So sine of 1 over x, I encourage you to go graph it in Desmos, and you'll see that as x gets close to 0, the function just oscillates infinitely many times. The limit doesn't exist. The limit doesn't exist. So the intuitive definition of a limit is just not sufficient. And that's why you have to talk about the precise definition of a limit. And I'm really, really hoping that your Calc 1 instructor spent a good amount of time talking about this and helping you make sense of it, because in my opinion, a lot of the practicality of a limit boils down to this definition, because it's talking about tolerances and approximations converging to exact values. That's really what this is all about. So here's the statement. Um, so let f be a function defined on some open interval that contains a, except possibly at a, it doesn't need to be defined at a. Then if for every number epsilon greater than 0, there's a corresponding number delta greater than 0, such that if x is close to a, then f of x is close to L, then we say that L is the limit as x approaches a of f of x. All right. Oftentimes, epsilon is called the tolerance. I talked about that earlier. It's a tolerance or a maximum error. And here's the picture of it. So essentially what this is saying is, hey, when x is in here, f of x has to be in here. This is what we call this thing right here. Let me use blue. This is what we call the epsilon band. So it's basically a band, and the band has length 2 epsilon, or maybe I should say width 2 epsilon. It's epsilon up and epsilon down from the line L, okay? And what we're doing is we're basically saying, hey, no matter what epsilon you give me, I can find a delta. Delta is this distance right here. Delta is those two distances. If you give me an epsilon, I can find a delta where as long as you're delta close to A, f of x will be epsilon close to L. That's really what it's saying. And if you can do that for all epsilon, for every epsilon, every possible tolerance, then the limit exists. And that's what your function is going to. That's what the limit is. Okay. Now let's talk about a limit at infinity. So a limit at infinity is a very, very similar idea, except now instead of approaching a point, you're letting x get arbitrarily large. That's what's happening here. You're letting x go to positive infinity and seeing if your function converges to some number. That's what you're doing. Or you could go to negative infinity too and see if x converges to some number. That's this, negative infinity, positive infinity. Okay. This is also how you define asymptotes. So if such a limit exists, so if the limit as x goes to infinity is equal to some number, that's how you define a horizontal asymptote of your curve. That's literally the definition of a horizontal asymptote. I like this picture in particular. I think the picture is very, very clear. What we're saying is that for any given tolerance, epsilon, I can find a point n such that as long as we're past n, then the distance between the function values and the limit is small. That's what that says. So here, if you look at this function, this blue curve, well, pretend we're given epsilon, we're given a tolerance. Maybe the tolerance is like 0.0001. Okay, so somebody's like 0.0001. And the question is, how far out do you need to go until your function is within 0.0001 of L? And that's this number n. So you have to find the n. Generally speaking, you're given a tolerance, and you need to find how far out you go. And then after that point, your function remains in the epsilon band forevermore. All right? And if you can do that for any given tolerance, so for any given tolerance, you can find a point where your function never leaves the epsilon band after that point, then the limit exists and your function goes to that limit. All right? Okay. So those are the precise definitions. Then what you get is you get all these really, really nice limit laws. So I'm just going to breeze through these. I'm sure you're all very comfortable with these. The one thing I will emphasize here is that in order to use these laws, the limits must exist. The limits must exist. And I harp on my Calc 1 students about this a lot because it's very tempting to want to just use these laws. But you can't use these laws or use these theorems unless you've satisfied the hypotheses. Yeah, you have to satisfy the hypotheses before you can use these conclusions. So if this limit doesn't exist or this limit doesn't exist, then you can't use this. You can't use this. You have to know they exist first. Then you can use this result. And this result is really, really nice. So these two properties they combine to form what's called linearity of the limit operator. It's basically showing that the limit operator enjoys the properties of linearity, which basically means, hey, if you have the limit, actually, see, I should put parentheses here. If you have the limit of a sum or a difference, you can split it up into a sum or difference of the limits. And if you've got the limit of a constant multiple of your function, then you can pull the constant multiple out of the limit operator. That's called linearity. All right. Then you get these other really nice limit laws. So this one is particularly nice. The limit of, see, I really should change these. The limit of a product is the product of the limits. Everyone loves this one. It's also the most abused because, again, you can't split this limit up into a product of two limits unless both of these limits exist. It has to exist before you can use this, okay? Keep that in mind. It has to exist. They both have to exist, not it, but those, them. They have to exist. Same thing for limit of a quotient, right? You can move the limit operator into the top and the bottom, but only if the individual limits exist. We also have another proviso here. The limit of the denominator can't be zero because you can't divide by zero. Or I should say, it's not a good idea to divide by zero in this case. Okay. All right, then you get some other limit laws that are nice. I'm not going to dwell on these ones, but they're all the ones that you remember from Calc 1. Limit of a constant is that constant. Limit of x is just the number you're approaching. Same thing if you're doing x to the n, and yada, yada, yada. So other limit laws. I'm going to do this one example. This one is one that you're all probably very comfortable with. I just want to emphasize a couple of points on it. So we're going to find the limit as x approaches -2 of this function right here. And one of the common limit techniques that you use is to factor and cancel. So down here, this is actually a sum of cubes. And a sum of cubes factors into this right here. You should know the formulas for a sum of cubes. All the general like factoring formulas. Difference of squares, difference of cubes, sum of cubes. You want to know those ones. Why do you want to know those ones? Because, well, let me ask you. If you have a polynomial that's degree 4, what do you know you can do to it? Hmm. Hmm. Oh, that's right. You can factor it. You can factor it because it's literally the fundamental theorem of algebra. That's why you learn the formula for the sum and difference of cubes. Because if you've got a cube, it can still be factored. And when you factor a difference or a sum of cubes, look at what you get. You get a linear factor and an irreducible quadratic factor. That's why you learn those formulas, because you know you can always get down to those cases where you've got cubes or quadratics. If you've got a quadratic, then you use the quadratic formula solve that, set that equation equal to zero, or set that expression equal to zero, solve for x, and you've got the factor, or the zero, I should say, the zero. Anyway, back to this. Factor and cancel, factor and cancel. Now we can actually take the limit, and at this point we can actually plug in the number to get 1 over 12. One thing I want to emphasize here is through this whole process, the limit operator remains because we have not taken the limit yet. So it's critically important to keep this right here. Think of that limit symbol as the letter F for a special function box called the limit operator. And what this box does is you drop a function into it, and it tells you where that function is going as x approaches a number. So again, this thing here is a function. It's a function. It's a box. And when you drop functions into this box, it tells you where they're going as you approach some number dependent on where the box wants the number to go. So through this whole process, we haven't actually applied the limit operator yet, right until this very last moment. And that's the first time you can actually apply the limit operator. And then when you do, you get a number. You get a number, and that number ends up being 1/12. Woohoo! Okay, all right, so that's one example. Another limit law you want to be comfortable with is the squeeze theorem. The squeeze theorem gets used a lot. It's really kind of a special case of a comparison theorem, but that's really what it is. All right. Okay. Yeah, this one I won't dwell on too much. Basically, if you have this relationship when x is near a number, it doesn't even have to be near a number. It can even be at infinity. And you know that the limit of the outer functions is the same, then the limit of the inner function has to be that number as well. That's what it is. That's the squeeze theorem. Okay. The derivative. So the derivative is something you spend a significant amount of time in Calc 1 developing. You definitely need to know the definition of the derivative, all the definitions of the derivative. This is basically it right here. You can write it in equivalent ways. The derivative is just the limit of the difference quotient. That's what these are. That's the difference quotient. And you take the limit as the denominator goes to 0. And that's what you're doing. Geometrically, what's happening there is you are looking at the slopes of these secant lines. So this pink line or purple line here is the tangent line to the curve f of x. That's the tangent line. And what you're doing is you're looking at secant lines. So this is the slope of a secant line, maybe this one. And what you're going to do is you're going to let those secant lines approach the tangent line using the limit operator. And then, hey, if that limit exists, you can actually get the slope of the tangent line. Okay, won't dwell on that too much. Now let's talk about the operation of differentiation. So when I teach Calc 1, and even when I teach Pre-Calc, and when I teach Calc 2, I do like to talk a bit about operator theory. Because again, these things are functions, and you are using these functions to do things to other things. So it's good to, oh no, hold on, wait. All right, let's try that again. So, where was I? Oh yeah, the operation of taking a derivative. So, when you take a derivative, that operation is called differentiation, and it is actually an operation. So you can think about it as like a function process, right? So when we differentiate a function, what we're saying is quite literally computing the derivative of f by taking the limit as h goes to 0 of the difference quotient associated with f. So that's called differentiation. And to indicate that we want to do that operation, we use the differential operator or the differentiation operator, which is denoted d dx. And we write d dx of y is equal to dy dx. So in this case, kind of like I was mentioning in the general theory of functions, d dx is the name of the differentiation operator. It's the stamp on the side of the box that says what the box is going to do. In this case, the box is going to differentiate. All right. I want to take a moment to just kind of emphasize this notation because I find that it gets to be a little bit confusing if you haven't emphasized it a little bit. So again, this symbol here is the operation of differentiation. It's saying to do that operation. Whereas this symbol here is the output of the differential operator. That is the output that you get once you differentiate a function. So This is why I indicate it like this. D dx is like f, and y is the input of the function f. And then what you get out is you get out f of x, essentially, right? So you can think of this as like f of x equals f of x. In this case, this is the function, this is the input, and then this is the output. Okay, so those two symbols mean different things, and they're very particular in what they mean. Okay, there's also a whole bunch of other notations for derivatives. I won't dwell on these ones too much longer, but you're going to see a bunch of these for those of you that go on to Calc 3, and for those of you that go on to higher math courses, you'll see all of these possible definitions, or sorry, notations for a derivative. All right, but enough about that. Now we get all the delightful, delectable differentiation rules. So these are the differentiation rules that everybody knows and loves. I forgot to emphasize these ones specifically, but these two correspond to linearity of the differential operator. So again, this operator, ddx, is linear. So if you want to differentiate a sum or a difference, you can differentiate the individual pieces and then add or subtract the results. Same thing here, you can pull out constant multiples through the differential operator. Yeah, so differentiation rules. These are all the rules that you know and love. The power rule, everyone's favorite. I'm assuming you know this one well. The product rule, f prime g times f g prime. I'm sorry, plus f g prime. The quotient rule, f prime g minus f g prime all over g squared. And then you get the chain rule. The chain rule is the most important differentiation rule. So make sure you are very comfortable with it. We will use it a lot. You have used it a lot, and you'll use it again in the future. This one you have not learned yet if you took Calc 1 at SMC, because we use the late Transcendentals version of Stewart, Clegg, and Watson's book. We're going to get this result in chapter 6, but it's a good thing that I like to include it here just for completeness. The derivative of an exponential function is ln of the base times a to the x. And in particular, this is one of the reasons why the exponential function is called the natural exponential function, because the derivative of e to the x would then be ln of e, which is 1, times e to the x, and you just get e to the x. So e to the x is its own derivative. It is its own derivative. Okay, here's an example. I'm just going to throw up this example to see something that you should be kind of comfortable with. If you had to differentiate this, there's going to be some stuff involved. There's a product involved. There's also chains involved. So this is kind of a combo derivative. And when you use the product and the chain rules, this is the derivative you get. So you do want to be comfortable with differentiation. If you need some more practice with differentiation, frankly, just make up a crazy looking function. Maybe it's got a bunch of products and stuff in it, and then try to differentiate it yourself. And then to check your answer, just go to Wolfram Alpha, enter it in Wolfram Alpha, and say literally differentiate, and it'll give you the answer. So that's one thing to keep in mind. All right, so now let's talk about linear approximations, and these are really important. And in this class, we're actually going to expound upon these ideas. And I know that when I teach Calc 1, when we get to this section, I like to introduce a little bit of flavor from what we learn in Chapter 11 from Calc 2. So Chapter 11 in Calc 2, in particular, the last couple sections, are like a generalization of this idea. So what is a linear approximation? It's basically this. Let's say you've got a function that's differentiable at a point, then we can write the equation of the tangent line like so. That's the equation of the tangent line written in a point slope form, right? Now, if you basically if you basically move things to one side, what you really get is you get what's called a linear approximation of f at the point A, or linearization of f at A. So in other words, our function f of x is approximately this value here when you're near the point A. So this is all about being near the point A. And when you're near the point A, you can instead use this line to approximate values of f. Okay, that's the idea, linear approximations. Again, we'll expound upon it later, but it is an important idea, so I wanted to at least touch on it. All right, now I want to briefly talk about transcendental numbers and functions before moving on to integral calculus. So transcendental numbers and functions are a good motivation for why we study calculus and why we learn these things. Because there are some really bizarre, I don't want to say bizarre, important and maybe funky numbers. So for one, an algebraic number is a number that is a solution to a polynomial equation with rational coefficients. So these numbers are actually pretty nice, relatively speaking, because computers can encode these numbers exactly. So for example, the number square root of 2 is an easy example. Square root of 2 is algebraic because it's the solution to this polynomial equation. If you solve this equation for x, you get the square root of 2. And the thing about this is the coefficients here, so maybe I'll use this. The coefficients here are rational numbers. So the coefficient here is a 1, and the coefficient here is a -2. So using those two coefficients, you can basically tell a computer what the square root of 2 is exactly. So you can encode these numbers in a way that a computer can digest easily, and it can digest them in an equal way. Like the computer can actually see this number in an exact way using this polynomial. That's the idea. Now, a transcendental number is different. So a transcendental number is a number that does not have this property. It's a number that is not a solution to a polynomial equation with rational coefficients. So classic examples, pi, e, ln of x for almost every x. These are transcendental numbers, meaning that you cannot come up with a polynomial with rational coefficients that gives you these numbers as a root or as a zero. It's not possible to do so. So the existence of these numbers necessitates the development of numerical algorithms to approximate these numbers, which I'll talk about in a moment. So, for example, a transcendental function is a differentiable function that doesn't satisfy a polynomial equation with rational coefficients. So it's the same idea, but instead of being a specific number, it's like a general function. Um, Another way of viewing it, something we'll talk about again later, is it can't be expressed algebraically using a finite amount of terms. So one of the reasons that we like things like Taylor series and Taylor polynomials is because they let you get at transcendental functions in a very, very nice way, meaning you can work with them in a nice way. At the end of this course, so literally like the second to last section of this course, we will find polynomial approximations of all of these functions. And those approximations are quite literally how computers see these functions. A computer cannot see the cosine function, but it can see an approximation to it, and it can see really, really good approximations to it, but it can't see it itself, all right? The other thing about these functions, most of the values of these functions, most of the outputs that you get are transcendental. They're transcendental numbers. So these functions are spitting out tons and tons of transcendental numbers. Um, for example, if you take cosine of any rational number, it'll be transcendental. Cosine of 1/2, cosine of 3/4, cosine of 1. Anything except for cosine of 0. I should say r not equal to 0. Here, r not equal to 0. It'll always be transcendental. It'll always be transcendental. Cool stuff, weird stuff. So like, what is a transcendental equation? A transcendental equation is an equation that contains transcendental functions or transcendental numbers. But again, in general, transcendental equations cannot be solved algebraically. So when you see something like this, and you're like, what's the solution to that equation? What is x? Solve for x. What I'm telling you is there's no algebraic way to do it. It transcends algebra. That's why we call them transcendental, because this type of equation transcends algebra and you cannot use algebra to solve it. It is impossible to do so. However, what you can do instead is you can approximate the solution using numerical methods. And the first one of these that you learn is the Newton-Raphson method. So I'm hoping that your teacher, your Calc 1 professor, took a decent amount of time on this section because that is the first numerical approximation method that you all get to learn. Computer scientists, you're going to learn a lot of these methods. Engineers, you're going to learn a lot of these methods too. There are literally thousands of them. So it's not just one, not just two, literally thousands of them. And they vary depending on the application and what you're going for. So some of these algorithms are very, very short. I'm sorry, what I'm saying, short. Some of these algorithms take a long time to run, and some of them are much faster. The question of which one's faster and which one is the most efficient, that's for the computer scientists. So dig into that when you get further along. Also, a popular application is finding the solutions of differential equations, ordinary differential equations and partial differential equations. All right. Okay, on that note, it's time to take a break. So go ahead and take another break. I'll play the music. All right, welcome back. So I hope you all had a nice break. We've covered precalculus, we've covered differential calculus. Now let's talk a little bit about integral calculus. So now this is where we get the integral, okay? Here's the overview, just a quick review of the definite Riemann integral, then the fundamental theorem of calculus part one, fundamental theorem of calculus part two. We'll talk about the integral operator, then properties. Oh, why is this split? That's weird. You. Properties of the definite Riemann integral, then the power rule, the substitution rule, a brief conversation about linear functions, and then we're going to top everything off with this very, very complicated theorem that I like to discuss in my Calc 1 courses and Calc 2 courses called the Riesz-Markov-Kakutani representation theorem. This theorem is not a theorem that your previous calc instructors talked about, I'm almost certain. I like to discuss it because it is a graduate level theorem that, in my opinion, motivates the study of integration. I'm always of the opinion that there should be meaning behind what you're studying, and you should care about why you're studying it. Like, why, who cares? Like, who cares about any of this stuff? Why learn integral calculus? Why learn differential calculus? Why do people devote their lives to it? Why do you have to go through years of education learning this stuff? And in my opinion, this theorem is a really good motivator for that because it kind of tells you what integration is really for. And that's why I like to talk about it. Again, you don't need to have this memorized or know this. And when we get to it, it uses a lot of like high mathematical ideas that you don't need to know, but I at least want to talk about it so that way you can get some context for why integration is so important. All right, so let's start with the definite Riemann integral. This is the definition of it. So let's say you've got a function defined on some closed interval, and you're going to take a partition of that interval. A partition is just a list of points in the interval that is increasing. So basically an ordered list of points inside the interval. We're going to let delta x sub I be the length of the subintervals determined by this partition. And we're going to let x sub I star be a sample point taken in the subinterval given. Then the definite Riemann integral of f from a to b is the number given by this value, provided that that limit exists as a finite number for any partition of P and any sample point too. If this limit exists, then we say that the function is Riemann integrable, okay? Let's see, do I want to jump ahead of myself here? Let me go here. I'll go to this one. So if it turns out that f is indeed integrable, then for convenience, we often just choose delta x sub I to be uniform. So that way we have this formula. So this is the formula that many students remember. But I like to talk about this formula in the beginning because your partitions do not, or sorry, your partition does not need to be uniform. And what that means is that the distance between these points does not need to be equal. But if it turns out that your function's integrable, you can just take the distances to be equal just to save yourself a headache. So rather than talking about the limit as the biggest subinterval goes to zero, you can talk about the limit as the number of subintervals goes to infinity. Because as n goes to infinity, the length delta x goes to zero. There you go. Some other things to keep in mind. Oh yeah, I'm going to go to this slide for this. Whenever you see a formula, you want to make sure that you understand every single piece of that formula, and you could identify where each piece comes from, and you want an intuition for what it represents. So I'm going to talk about that here and now. Uh, how do you actually compute this integral? Well, what you do is you start with an approximation, and then from that approximation, you take finer and finer approximations. And then basically, as you take the approximations to get closer and closer, you converge to this integral value. So let's look at each piece. Um, f of x sub I star, well, maybe I'll start even smaller. X sub I star is a sample point. It's a sample point that you pick in every subinterval. So like here's in the first subinterval, here's the first sample point. In the second subinterval, there's the sample point. In the third subinterval, there's the sample point. So x sub I star is just a sample point. All right. F of x sub I star is the function value at that point. So in this picture, it's literally the height of these lines. That one, that one, that one. So quite literally, the height is f of x sub I star. Delta x is the width of the subinterval. It's the width of all those things right there. And so that means f of x sub I star times delta x is the area of one of these rectangles, the ith rectangle. So I guess maybe if I did this one, I should, there you go. All right. So this expression right here is the area of this rectangle. And then what we're going to do is we're going to add them all up. So when you add them all up, you add up the area of these rectangles, you get an approximation to the area under the curve. It's not equal to the area under the curve, it's approximate. It's approximately the area under the curve. Then what you do is you take the limit as the number of subintervals goes to infinity. These rectangles get skinnier and skinnier, and then in the limit you get the exact value, and the exact value is the area under that curve. Woohoo! Yep, I love that. Okay, so that's the definite Riemann integral. Because the Riemann integral is defined as a limit, it has a precise definition using the formal definition of a limit. So this is the formal definition or the precise definition of the definite Riemann integral. What we say is that a function f is Riemann integrable if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that this distance is small for any partition of the subinterval as long as the longest subinterval is smaller than delta. And this has to be true for all possible sample point choices. All right. Now, what does this really mean intuitively? This means that the integral can be approximated to any degree of accuracy by a Riemann sum as long as the number of rectangles is chosen to be sufficiently large. That's the idea. So again, this is why the definition of absolute value is so important. This gobbledygook here that looks really confusing, this is the integral. That's the exact value. This is a finite Riemann sum. That's an approximation. This is the distance between the approximation value and the exact value. And this is saying that that difference will be small. It will be small. And if that's true for any possible tolerance, epsilon, then your function is Riemann integrable. That's what that means. Oh, man. Clouds keep going over the sun. It's like bright and then dark and then bright and then dark. Okay. Now where am I? Okay, so that's the definition of the Riemann integral precisely. Now let's talk about the fundamental theorem of calculus, part one. Part one is the most important part. Part one is the part that actually connects integral calculus with differential calculus. But what's funny is part two is the one most students remember because part two is the part that lets you compute integrals. That's really it. But this is the one that was profound. This is the one that Newton and Leibniz came together, or their theory came together, and you got to see how they were connected. One of the first things I'd like to talk about when I introduce this subject is that this theorem deals with functions of this form. And you want to make sure you are very, very comfortable with functions of this form. This is what I like to call the area so far function. Yeah, I do. Okay. So here with this function, notice that the variable of integration is x, not t. The variable, I'm sorry, variable of the function, my bad. The variable of the function is x, not t. So the thing that is changing in this function is the upper bound of the integral, not t. Okay, it's x. So this is, yeah, the input of this function is the upper bound of integration, not the function f of t. Okay, so this is why I call it the area so far function. What this function is giving you is it's giving you the area under the curve of f of t from a to x. And as you change x, it's like moving the upper bound of integration. That's what's going on there. I have a Desmos example here. I'll go back to my laser pointer. You're more than welcome to explore that on your own. I'm not going to dwell on it here because you are supposed to talk about it in Calc 1. If you want to discuss it more during our meetings, I'll be happy to, but you've got to make sense of area so far functions because they're critical. They are literally what FTC1 deals with. And this is the statement of that theorem. So FTC1 says this. It says if you've got a continuous function on the interval a to b, then the area so far function is an antiderivative of f. That's what it says. So in other words, if you differentiate g, i.e. you differentiate this area so far function, then you get the function f back. Or I'm sorry, then you get f of x back. So using Leibniz notation, it's really quite beautiful. It's just like that. Remember, the derivative of the integral is f of x. So I want to talk about this a little bit because I'm not sure how much your professors or instructors dwelled on it, but it's good to make sense of it. Intuitively, FTC1 is saying that the instantaneous rate of change of the area so far function is the height of the function at that moment, x, intuitively. So I want you to ponder that for just a minute. Mm-hmm, mm-hmm, mm-hmm. Yeah. Okay, that's literally what this is saying. The rate of change of the area so far function is the height of the integrand at the moment x. That's what it is. And this makes sense geometrically because basically what it's saying is that at every point, you're going to add the length f of x. And that is how fast the area is changing. You're adding f of x at every step, and you're adding f of x at every moment. So the rate of change of the area is that height per moment, literally. And that's what this is saying. That's FTC1. That's the fundamental theorem of calculus. Then there's part two. Part two is a different statement. Part two says this. It says, if your function f is continuous, then the definite integral from a to b of f of x is equal to the difference here, where capital F is an antiderivative of little f. So in other words, capital F prime is little f. All right. Now, the intuition behind this may not be immediate, but you can get intuition by restating the theorem as the net change theorem. So this is essentially equivalent to that theorem. But it says if you've got a differentiable function, then the integral of the derivative, or I should say the integral of f prime of t is equal to the net change of f, right? This is the net change. That's the net change of f. And so what this is saying is this. Oh, wait. Yeah, I'll come back to this. Yeah, this is the intuition. I'll say this right now. FTC2 is saying if you add up all of the instantaneous rate of change at every point in an interval, then you're going to get the net change of the function over that interval. So ponder that for just a minute. Yeah. And then what I want you to do is say this part out loud. Ponder this part for a minute. Add up instantaneous rate of change at every point. You get the net change. Mm-hmm. Yep. Okay. This is the connection between the net change theorem and FTC part two. It really is equivalent because remember in the statement of FTC2, we're assuming capital F prime is equal to F. So FTC2 says, hey, this is equal to this which is equal to this. That's what it's saying. So it's the same theorem. Okay, now, now let's talk about the integral operator. Here we go. So just like the limit operator and just like the differential operator, the Riemann integral is an operator. It's an operator, much like the others we've seen or you've seen in your courses before. The operator is denoted with this symbol. This is a function. This is a function, and what you do is you drop functions into it, and it spits out a number. It spits out some number. So this is a box. This is an integrating box. And when you drop things into the integrating box, it tells you what the area, the net area under the curve of that function is. Okay? Do this real quick. There we go. This is okay. So now I can actually talk about what a functional is. So the Riemann integral is what we call a functional. A functional is a function that takes in other functions and spits out a number related to that function. That's what a functional is. It's just another name for it. In this case, the integral operator takes in a function and it outputs the net area under the curve of that function. There you go. Okay, so think of the integral as an operator. It's a process. It's like a thing that you can do to functions. It's a box that you can drop functions into, and it will give you information about that function. It'll give you the area under the curve, right? That's basically what it's doing. That's why the general theory of functions and functionals and operators is important to make sense of. Okay, now we're going to get a ton of the properties of the definite Riemann integral. I'm not going to dwell on these very long. These are all the properties you know and love. If you switch the bounds, it changes the sign of the integral. That's basically because you're scanning backward now. Another way to think of the integral is as a scanning machine. It's a scanning machine. It scans from left to right. But if you scan from right to left, it's going to invert the sign of the result. It's going to make the sign the opposite because you're scanning backward. All right. If you integrate from a point to itself, your integral is 0 because delta x is 0. So the integral of a function at a point or over a point is 0. The integral from a point or from a number to itself is 0. There you go. This is a really important one, actually. So the integral of the unit function, just the constant function 1, otherwise written like this, just gives you b minus a. It just gives you the length of b minus a. So that's super important because if you add up all the change in x, it gives you the length of the interval, which makes sense, right? Now, more generally, instead of integrating the function 1, if you integrate the function c, then what you get is you get the area of a rectangle with base b minus a and height c. That's what you get. So this just gives you the area of a rectangle. All right. Oh yeah, so this one is another important interpretation of the Riemann integral because what it's doing is you can think of it as giving you the weighted length of the interval a to b, right? The weighted length of the interval a to b. In fact, maybe I should even say like this one instead. So when you look at this integral, you can think of it as basically providing a density to every point in that interval. And you're adding up all of those densities. And then when you add up all those densities, you get the result afterward. So in some senses, you can think of this as a density function, right? Density function. And again, when you get into, you talk a little bit about it in section 5.4, which is on work, and you'll talk about it even more in Calc 3. So for those of you that are going to go on and take Calc 3, you're going to talk about this idea at length. You're going to talk about density functions and adding up densities at every point. Yeah, there we go. Other nice things. So linearity, the definite Riemann integral, the Riemann integral is a linear operator. If you integrate a sum or a difference, it's equal to the sum or difference of the integrals. And you can pull constant multiples out of the integral operator. And so this actually means that the Riemann integral is what we call a linear functional. It's a functional that enjoys the property of linearity, these two ideas. All right. Notice we had the same thing with the limit operator and the differential operator, right? Like you could do this, and you could do this. Okay, here's another good one. If you want to integrate from A to B, you could integrate from A to C and then integrate from C to B. and the results are the same, that's a nice one. You can cut up the integral into pieces and you still get the same result. Then you have comparison properties. So these are we're going to see a lot actually when we get to section 7.8, I believe. Yeah, we'll use these in section 7.8, yeah, 7.8 on improper integrals. So for one, if your integrand is positive or non-negative, then your integral has to also be positive or non-negative. So basically, if your function is always above or on the x-axis, then the area underneath it has got to be positive. That's basically it, or at least non-negative. Furthermore, or moreover, I should say, if you have this order relationship between two functions, so f is always greater than g on some interval, then the integral of f is always greater than the integral of g on that interval. And that just makes sense intuitively. That makes intuitive sense, right? Because what you're saying is the area here, if f is bigger than g, then the area under f is greater than the area under g. Make sense? Makes sense. Then you get these nice bounding properties. You actually have to use these properties to prove the fundamental theorem of calculus, part one or part two. I can't remember. Let me think. Part one, yeah, part one. Use this to prove FTC part one. So if your function is bounded below and above, then the rectangle with this area is less than the area under your curve, and the area under your curve is less than the rectangle with this area. It's another important property. You can basically bound this area between the area of two rectangles. That's what that's saying. Then we get, oh yeah, everyone's favorite, the power rule, right? The power rule. So if you want to compute an antiderivative of a power function, as long as n is not -1, then you just do that. Everyone's favorite. Then there's the substitution rule. So the substitution rule is a technique that you learn in Calc 1 near the end for computing or evaluating integrals. You're going to use this rule a lot, and very soon this will be a step in the integration process that just gets skipped. Okay, so make sure you are comfortable with it. We can practice it if you would like. Actually, I think I have an example right now, so we're going to do that right now. What's also nice about this particular rule is that it asserts that it's permissible to operate with dx and du inside the integrals as if they were differentials. So this kind of gives you that justification. So here's a good example, and maybe this one I will let you try on your own. So try to do this one on your own at home. See if you can evaluate this integral using a substitution. I'll throw up the thinker and say, what substitution do you think you could make? All right. Now, say it out loud. What's the substitution you're going to use? All right, now try to calculate it on your own. See if you can evaluate this integral. It is a definite integral, so you should end up with a number at the end. All right, now let's do it together. We're going to let u be x cubed plus 5. That's the substitution. Let u equal x cubed plus 5. Then du equals 3x squared plus dx. That's exactly what we want because that appears in our integrand. And now here's an important point, and I will say this now and I will say it again in the future. We have a definite integral. So if you change the variable of integration, you must change the bounds. You must change the bounds. You're more than willing to ask me about this. Students usually are wondering like, oh, do we have to change the bounds? The short answer is yes, 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 yes. Just change the bounds. Just change the bounds as you go along if you have a definite integral. But we can talk about that more if you are interested. Here's how you do it. You use the literal relationship that you chose, the relationship between x and u. So when x is 1, u is equal to 6. And when x is 2, u is equal to 13. So the area under this curve, or I should say the area under this curve from 1 to 2 is equal to the area under this curve from 6 to 13, right? If we change the function, the area will change unless we account for the bounds. Now you've got a simple integral to do. You can use the antiderivative, use the power rule to compute the antiderivative, and then you get this, voila. All right, now rounding things off, we're almost done here. Let's talk about some profundity. So you've explored the fundamental theorem of calculus. You learned how to compute antiderivatives using a lot of different techniques. We're going to learn a lot more in this class too. We've intimately studied the mechanics of the Riemann integral. You want to know how the Riemann integral actually works. We'll review it again in this class, but the mechanics of it are critical. Why is this important? Why should we care about this? Why should we learn about the integral? And so on and so on. Well, let's talk a little bit about linear functionals. So a functional is just a function whose domain is a space of functions, and its range is a subset of the real numbers. So a functional takes in other functions, and it spits out a real number related to that function. That's what a functional is, okay? So you put in a function to this box, and it spits out a number related to that function. Remember, that's just the general idea. A linear functional is a functional that enjoys the properties of linearity. So something like the um, integral operator, the differential operator, the limit operator. This is how you write it um, in precise notation. So let's say we have a linear functional L. Well, if we put a sum of functions into it, we can do L of f plus L of g, and the result is the same. Or if I put in a constant multiple of a function, then I get, so L of c times f is the same as c times L of f. So you've actually seen and worked with three linear functionals already: the limit operator, the differential operator, the integral operator. So in this case, L is this limit guy. And what you do is you put f into the limit. Or L could be this guy right here, the differential operator, and you put f into the differential operator. Or L could be this integral, and you put f into that integral. And that's the functional in that case. That's the linear operator. All right? That's what a linear functional is. You put functions into it, and it spits out real numbers. Okay? So here is a very, very complicated theorem. This is the Riesz-Markov-Kakutani representation theorem. And I like to talk about it because I feel like it motivates why we study integration and integrals. So the theorem is named after Frigyes Riesz. He introduced it for continuous functions on the unit interval a little over 100 years ago. And then Andrei Markov extended it to what are called non-compact spaces. And then Shizuo Kakutani extended it to compact Hausdorff spaces in 1941. So again, you don't need to know what all of these terms are. You don't need to know what a Hausdorff space is. You don't need to know what a compact space is. I'm going to try to make this a little simpler. But what the theorem says is this: if you've got a nice space, okay, then for any positive linear functional, so kind of like the ones we've been working with, or yeah, kind of like the ones we've been working with, if it's defined on that nice space, meaning the functions are nice enough, then there's a unique Borel measure such that your linear functional can be written as this integral for all f in that nice space. Okay, so I'm assuming you all are thoroughly confused, which is a good place to start. A good place to start. Again, this is a graduate level theory, graduate level theorem, but it motivates why we study integration. And here's the big idea. Maybe it's easier to look at it just in terms of Riesz's interpretation. So every continuous linear functional defined on the space of continuous functions on the unit interval can be represented as an integral. So what is the big idea here? The big idea is what I say down here. The definite Riemann integral is like our canonical measuring device. That's what it is. So what I mean by that is if you want to measure something that's quote unquote nice enough, something like volume or arc length or surface area or the charge of a particle or risk or probability or efficiency or accuracy or class attendance or all of these things that you want to measure, then the tool that you're going to use to measure them is a Riemann integral. That's what it means. The Riemann integral is our measuring device. I can even give you an example here. Okay, here's a measuring device, right? There you go, tape measure. Okay, so if I draw a line, this is usually what I do in class. If I draw a line somewhere, right, I just draw some random line on the board and then I go, okay, how long is it? Okay, it looks like it's about 10 inches, okay? But then when I look closer, I'm like, oh wait, the line is actually about, if I look at the smaller tick marks, it looks like it's actually like 9 and 7/8, right? Oh, but wait, when I look even closer, if I look at the smaller tick marks, it's more like 9 and 15/16. Oh, but wait, there's even smaller tick marks, and when I look at those even tinier tick marks, it looks like it's 9 and 31/32. That's integration, my friends. That's integration, my friends. What you're doing is you're letting the size of the subintervals shrink, and then you're getting a better approximation of the actual length, right? That's the process of integration. So the integral is your measuring device. And whatever you want to measure, as long as that thing you want to measure is quote unquote nice enough, that's what all this stuff is about. All this like Hausdorff and compact, that's defining the niceness. You're going to use an integral, the Riemann integral. So this is why you study integration. This is why you spend 2 classes, almost a whole year of your math education learning about integration, because in the future, when you all want to measure other things, you're going to use an integral. You're going to use an integral. You just have to figure out what you're going to add up to get the right result. And I don't mention it in this review, but if you remember from Calc 1, if you studied volumes, like volumes of surfaces of, volumes of revolution, right? Where you had to learn like the disk method and the washer method and the cylindrical shell method, you're basically utilizing this theorem. You want to measure volume, and so you're constructing a way of measuring it using the Riemann integral. You have to come up with the function, and then when you add up those results, you get the measure that you're looking for, the volume in that case. You do the same thing when you learn about work in section 5.4 and then again in Calc 3. You're basically adding up a force function. And when you add up that force function over some interval, you get the work done. So why do we study integration? Because the Riemann integral is our canonical measuring device. And so we want to know how to use it pretty darn well. Yeah, there it is. All right, we can talk more about this later if you're interested. On that note, let's play. So, with each one of these lectures is an associated activity, and we will do the activities during our meetings, and I will help guide you through those activities. Um, Hopefully they're fun. That's really where all the learning is coming from. This is like an introduction to the theory, introduction to the ideas, but you got to practice it, right? You got to get your hands dirty. So I won't droll on for too much longer. Thank you for bearing with this very, very long lecture. I hope you did take breaks in between. Again, the lectures are not usually this long, so don't worry about that. They're usually, it depends. They're usually like 30 to 40 minutes, I would say. The longest one, I believe, is like an hour and 20 minutes. So, but again, you've got the time. You can watch them in double speed if you want. I recommend making a viewing party, like, just call up your friends or your group members from class and watch the lectures together and ask each other questions. It's a good way to make the time go. All right. All right. So I'm excited to meet you all and work with you all. The next lecture is 6.1, and that's where we get into the content of Calc 2. All right. So thank you again, and I'll see you all next time.